Differentiation, exponentials. So differentiating an exponential function is probably the easiest that we have to do, because if we take the function y equals e to the x, then the derivative is itself. So it is the only function where the derivative is itself. But that would be too easy for us to differentiate if that's all that we were given. So more often than not, we're given e to a power where the power is a function of x, in which case we apply our chain rule and we differentiate our exponential, which is just e to the power, but then we also must multiply by the derivative of the power. So if we look at our maths tables on page 25, we can see that the only thing it says there is e to the x, differentiated is e to the x, but it also gives us then e to the ax is equal to a e to the ax. So in other words, if we differentiate the power ax, then we get a, and we multiply that by e to the ax. So if we have a look at an example, if we're given, say for instance, y equals e to the power of 5x, then the function within the function there is 5x, and the derivative of 5x is 5. So in other words, that would become dy dx is equal to, differentiate e, we just get itself, and then multiply by the derivative of the power, which is 5. So we tend to always write our coefficient first, so we'd say 5 e to the power of 5x. It's the same again, if we have y equals e to the power of x squared, then our power is the function within the function. And if I differentiate x squared, I get 2x. So therefore, my derivative of e to the power of x squared is itself multiplied by the power differentiated, which is 2x. So again, that can be written as 2x e to the x squared. And then if we have a look at one more, we have y equals e to the power of cos x. So again, our function within the function is the power. And if I differentiate cos x, I get minus sin x. So if I differentiate e to the power of cos x, then I get itself times the power differentiated, which is minus sin x. So again, that can be written as minus sin x e to the cos x. So if we look at natural log of x, we have to remember that log x to the base e is another way of writing natural log of x. And another one that's important to note is ln e is log e to the base e, which is 1. Now all our log rules are on page 21 in our maths tables. And sometimes these are easier to use than differentiating the function that we're given. In other words, we can sometimes apply our log rules first, tidy it up, and then differentiate. Or we can differentiate with whatever we're given. So let's have a look at what is our derivative of natural log of x. So if we're given natural log of x, then on page 25 in our tables, we'll see that the derivative is simply 1 over x. But of course, we're often given natural log of a function of x, in which case our derivative would be 1 over the function times the function differentiated. So we can see this over here in the right-hand corner, where we have natural log of x and the derivative is 1 over x. So if we have a look at an example, we can be given y is equal to the natural log of 5x, in which case then we would say the derivative is 1 over the function, which is 5x, times 5x differentiated, which is 5. So again, you can do as before, take out your 5x and differentiate. But of course that can be simplified because 5 over 5x becomes 1 over x, which is our answer. Now, if we had have applied the log rules first, then we could have said, well, y is equal to natural log of 5 plus natural log of x. Because if we look here on the top of page 21, we have log x times y can be written as log x plus log y, where the bases are the same. And now if I differentiate, well, the derivative of natural log of 5, well, that's a constant, so the derivative is 0. And natural log of x, well, that's on our tables there, page 25, is simply 1 over x. So you can see either approach will give you the same answer. If we have y is equal to natural log of x squared, well, again, I could say, well, my function of x is x squared, and therefore the derivative of x squared is 2x. So therefore, if I differentiate natural log of x squared, that's 1 over x squared times x squared differentiated, which is 2x. And 2x over x squared leaves me with 2 over x. But again, we could have spotted the log rules and said, well, y is equal to 2 natural log of x. Because if we go back to our tables, we can see that that is the third rule down there, where we have log x to the power of q, and that becomes q log x to the base a. So now if I differentiate, I get 2 times 1 over x, which is the same answer, 2 over x. If we have y equals natural log of cos x, well, again, our function of x there is cos x, so the function within the function. If I differentiate cos x, I get minus sin x. So therefore, if I differentiate natural log of cos x, well, that's going to be 1 over cos x times cos x differentiated is minus sin x. And therefore, minus sin x over cos x, well, that's simply tan x. So therefore, our derivative is minus tan x. So the third thing we want to look at differentiating in this video is a to the x. Now, if I have y equals a to the power of x, a is a constant. So it could be any number. Well, let's see what our derivative is going to be. And I'm going to show you using implicit differentiation what the derivative is. But again, I will show you in your tables then where we can find this derivative. So if I get natural log of both sides, that's going to allow me to bring down my power of x from our log rules. And now if I differentiate the left-hand side with respect to x, I'm going to get 1 over y times dy dx. So differentiating y with respect to x, remember, is dy dx. And differentiating a log function is 1 over y. And then if I differentiate x ln a, well, ln a is just a constant. So if I differentiate any x function with respect to x, and it's just 2x or 5x or 10x, then the derivative is always just the coefficient of x, in which case is natural log of a. So therefore that means that dy dx is equal to y times ln a, if I multiply both sides across by y. But of course y at the start was a to the power of x. So that means that the derivative is actually written as a to the power of x natural log of a. So in other words, if we go to our maths tables, page 25, we can see that if we have y equals a to the x, then the derivative is a to the x ln a and that can be seen directly under e to the ax. So if we have a look at an example, we could often find ourselves having y equals a to the power of a function, in which case the derivative would be a to that function of x times natural log of a times the function differentiated. So if we were given y equals 2 to the x, that means that our constant here is 2. So therefore the derivative is 2 to the x ln 2. And if we had y equals 3 to the power of x squared, well, again, a here is 3. So that would simply become then 3 to the x squared times ln 3 times x squared differentiated, which is 2x. So for each of these, we could be given a product, a quotient, or we could be asked to find the equation of the tangent, the same way we have done for all our previous functions that we had to differentiate. So if we were to look at 2 or 3 examples of these, then in our first example, we have y is equal to x squared multiplied by natural log of e to the x. So we could look at that as a product, or we could apply our log rules. So let's see if we took it as a product first. We'd have u equals x squared, therefore du dx is equal to 2x. V is equal to natural log of e to the x, therefore dv dx is equal to 1 over e to the x times e to the x differentiated, which is just itself. And therefore dv dx is e to the x over e to the x, which is simply 1. Therefore our derivative is u times dv dx plus v times du dx. And again, our product rule is page 25 in our tables. So we can see that up here. So then if I sub in, I have dy dx is equal to u times dv dx, which is just 1, plus v, natural log of e to the x, times du dx, which is 2x. But of course, natural log of e to the x can be written as x ln e, and ln e is equal to 1. So therefore, natural log of e to the x is simply x. So therefore that gives us dy dx is equal to x squared plus x times 2x, which is 2x squared. So we end up with x squared plus 2x squared is 3x squared. But of course, if we had spotted there at the start that ln e to the x can be written simply as x, well, that would give us x cubed. In other words, y is equal to x squared times, instead of ln e to the x, we said x. Then y would be equal to x cubed, and therefore dy dx is 3x squared, which is a much quicker way of doing the question. But as I said, you would have to spot your log rules at the start to see that simplification. Okay, so the second one then was ln x squared over e to the x. So again, you might look at this and go, oh, well, that's a quotient, because it's a function over a function. And therefore say u is equal to ln x squared. And of course then du dx can be written as 1 over x squared times the derivative of x squared, which is 2x. And 2x divided by x squared is 2 over x. And again, you could have spotted that as 2 ln x, which is again 2 times 1 over x. So applying your log rules or not. So v is equal to e to the x and therefore dv dx is equal to e to the x. So therefore our quotient rule is v times du dx minus u times dv dx all over v squared. And again, back to our tables. You can see page 25, it's the second rule down. So subbing in, we have dy dx is equal to v, which is e to the x, times du dx, which is 2 over x, minus u, which is natural log of x squared, times dv dx, which is e to the x. And then that's all over v squared, so that's e to the x squared. So what we need to do now really is tidy up. So I can see I have an e to the x common on the top. So if I take that out as being common, I have e to the x times 2 over x minus an ln x squared can be written as 2 ln x over e to the x squared. So e to the x will go into e to the x once. I have a fraction on the top, so I'm going to multiply the top line by x, which means I have to do the same to the bottom, because otherwise I'll have changed the value of the function. So multiplying the top line by x, I get 2 minus 2x ln x, and multiplying the bottom by x, I have x e to the x, because I had 1 e to the x left on the bottom. So last example where we're looking at finding the equation of our tangent. So here we're asked to show the slope of natural log of sine x over 1 plus sine x is equal to 2 minus root 2 when x is equal to pi over 4. So we don't have to get the equation, just the slope in this case, and our slope should end up being 2 minus root 2. So let's say our function y is equal to the natural log of sine x over 1 plus sine x. So here, because it's logs, I'm going to apply my log rules to make life a little bit easier for myself. So again, if I go to my log rules, then I can see again on page 21 that the second one down says if I have log of x over y, then I can write that as log x minus log y. So therefore this can be written as log sine x minus natural log of 1 plus sine x. And now applying my rule for differentiating a natural log function. So again on page 25, we know that it's 1 over x. So in this case, it's going to be 1 over sine x, but I have to multiply by the derivative of sine x, which is cos x. And then minus 1 over 1 plus sine x. And again, I must multiply by the derivative of 1 plus sine x, which is also cos x. So therefore, if I tidy that up, that's going to be cos x over sine x minus cos x over 1 plus sine x. And now if I sub in for x is equal to pi over 4, I can then get the slope. So we'll have cos of pi over 4 divided by sine of pi over 4 minus cos pi over 4 over 1 plus sine pi over 4. So making sure your calculator is in radians. Then if we sub in for cos pi over 4 over sine pi over 4 into our calculator, we end up with 1. And then if we sub in cos pi over 4 over 1 plus sine pi over 4 into our calculators, we end up with minus 1 plus root 2. So then simplifying that gives me 1 minus minus 1 is plus 1 minus root 2. So therefore our slope is 2 minus root 2 when x is equal to pi over 4, which is what they wanted us to show. Okay, so looking at questions, we're going to have quite a few questions based on these today. So on page 348, we're doing question 1, 2, 3, 4, 5, 6, 7, and 8 of the questions marked here in front of you. So a to the x will be done in class tomorrow, so that's part of this video, so you'll be able to use it.